Section 6.2. So 6.1, we derived all of these formulas. 6.2 and on, we're going to use this table on page 252. I'll refer to that in a minute. So 6.2 is on page 248, solutions of initial value problems. In this section, we want to get acquainted with this table that they have. For example, if I start with find the Laplace transform of e to the ax dx by using the definition, anywhere you see the word definition on the exam, you're going to literally go by the integral from 0 to infinity of e to the at times e to the negative st dt. That would be the integral from 0 to infinity e to the a minus st dt. That would be e to the a minus st divided by a minus s evaluated from 0 to n, taking the limit as n approaches infinity. That is the limit as n approaches infinity of e to the a minus s n over a minus s minus, if you throw a 0 in there, 1 over a minus s. Now, as long as this right here, a minus s, is negative, if the power is negative, it's going to push the exponential down. This will shoot to 0, meaning if s is greater than a. And what you're left with is 1 over, if I distribute the negative on the bottom, s minus a. Now, if I look at number 2, do you notice this says if this is f of t, and you apply the Laplace on that, guess what you'll get? F of s, which is the Laplace, that's 1 over s minus a. If I copied that down, this is number 2. So from now on, I'll start pointing those. If I apply the Laplace on e to the at, instead of doing all of that work, that answer is right there. And that condition, s is bigger than a, is provided. And that is on page 252, and that's provided on your test. This formula, what they did, they worked out everything that we did in section 6.1. We could derive all of this. You did most of it on the homework. Or I did most of it answering your questions when you ask for those. So this table is provided on the test. You don't need to memorize, you just have to know how to use it. Now suppose f and g are piecewise continuous functions of exponential order, and alpha and beta are constants. If you apply the Laplace on alpha times f plus or minus b times g, that would be alpha times the Laplace plus or minus beta times the Laplace. So the constants you could ignore and drag up front. If I want to find the Laplace on example, let's call it example A. If I glance at this, I notice that they gave us f of s. So I'm looking at this table, and the table is on page 55. I'm going to copy this down. It looks like s to a power. We're not going to use this anywhere, so don't worry about that one. But if I look at 1 over s to the 1, s minus a, 1 over s to the n plus 1, I notice the only one of those that have a power that is general is this, but this is not s minus a. I'll point that out afterwards. So I'm looking at number 3, and I copied number 3 in my notes. If you look at number 3, it's right there. And look at the notes. If you really pay attention to it, you'll notice that if this is f of s, this is really how you come back. We call it inverse. Meaning, what did you take a Laplace off to get this answer? So we're working backwards. Well, let's see how this works. Since this is equal, it works forward and backward. This is actually the right side. So do you notice that this right here is what? You don't have to, but I could write that as s to the 2 plus 1, right? To match it. That means n equal 2. So if n equal 2, do you see that I need an n factorial at the top to be able to undo this? N factorial is 2 factorial. Well, I can't just have that, except I am allowed to multiply by a constant, which is a 1. And wouldn't this right here be... So basically, I didn't write the notation. If I take the inverse Laplace transform, isn't that t squared? So not only am I going to go forward, I'm going to go backwards. All what you have to do is write by 3 on your test or your homework, and I need to see that. And that's how we do this. And if I decided to move to the next example and figure out where this came from, again, I'm looking in the book and I'm trying to figure out which of those match this. Well, I'm looking at, again, this is f of s. If I apply the inverse Laplace transform, that would be 4 times the inverse Laplace transform. Oh, that it looks like this. Of 1 over s minus 3, and that's going to be 4 times, and I'm going to go in and copy what I see appropriate. And if I look at 1 over s minus 3, 1 over s, it looks like number 2. That is e to the as, or at. That's e to the at. So if I go in there, and it's right there, number 2, by 2, it seems if I want to go back, this will be e to the opposite of that, to the 3t. And that would be my answer. I'd like to look at some examples from the book. I want to start off with problem number, and I copied this down. I want to start with number 2. Now, if I look at this table and I'm glancing at it and how this is done, so this we're going to ignore completely. I'm looking at something raised to a power and s minus a. Well, if I look at that table, I notice that a shift in s doesn't exist anywhere. There is s minus there, but it's added a number to it. This looks more like it. This looks like what I just saw. Now, this will take us some time if we're going to stick with this. Instead, this is something I'm going to try to get you to work around. If you see a shift, take care of that first. If you see a shift, keep in mind the answer is e raised. E will take care of that shift. So if I look here, I notice that the shift is a 1. So if I write e to the t, automatically what that does, that makes this 4 over s cubed. So this takes care of the shift. The a is right there. And now, all what I have to do is apply the inverse Laplace transform on the 4 over s. And now if I look at the table, 4 over s to a power, it's right there. 4 over, was it s? S cubed, even better. Well, can't you say this is 4 over s to the 2 plus 1? Which means I need the top to be what? 2 factorial. Can't I say this is 2 times 2 over s cubed, right? And now, if I would apply the inverse Laplace transform, right? That would be e to the t, a 2 in the front, times 2 over s cubed. I'm sorry. I did all of that work and I didn't even figure out what that is. What's the inverse Laplace transform on that? Wouldn't that be based on this? The inverse would be t to the n. Wouldn't that simply be t squared, or simply 2t squared e to the t? So something I want to get the hang of. I'm going to do this one more time. Not very pleasant, but it takes time. So I want to apply the inverse Laplace transform on this. If I could find it in the table, I'm in a very good shape. But normally that's not the case. Now here, I did find it in the table, but this is an exception. I found it in the table, and it looks like, and you could use this, there's nothing wrong with that. I'm just telling you what's going to work for you in the long run. It does appear to match number 11 identically. All what I need to do is modify it a bit. And this says, if you see s minus a raised to the n plus 1 and n factorial, that's t to the n, e to the at. So I could just say, you know what, that is really, so here I'm manipulating algebraically to match it with what's in the table. I could say that's s minus 1, and if I want to match it, it says n plus 1 and n factorial at the top. n plus 1, that's 2 plus 1. And I need the 2 factorial at the top. The 2 factorial is 2. Can't I say the 4 is 2 times that? And can't I take this 2, and this works in the forward and the backward Laplace, meaning in the inverse as well. That's 2. And doesn't that say that this is t to the n, e to the at? T to the n, t to the n, e to the a. Remember what a is, the shift. Minus that is 1t, and there it is. And n was 2 in this case. So this is how we would actually do it. I do want to point out one thing that comes up a lot, and that's something you should really consider. Something that we're going to be using for a while, and let me show you what it is. Okay. Another way of looking at this problem is for me to say, you know what? I have f of s equaling 4 over s minus 1 cubed. I could take care of this when I apply the inverse Laplace transform, and that's e to the positive 1t. If I do that, I just shifted this problem, and now it's simply 4 over s cubed. But now you're going to multiply those. And if I want the Laplace of this, I'm going to say that's 2 times 2 factorial over s cubed. And by using what I just did right there on number 3, so this right here, this shift would be by, that shift will be by 2, and by 3, the 2 will remain there. By 3, this will yield a 1 t squared. And that would be my answer if I am to apply the inverse Laplace transform on this function. It's going to take a bit of time for us to get the hang of this, but we have plenty of time. Let's look at the next problem. Okay, now, if I need this, I'll get it in a minute. Let me copy. This is number 14. It just needs the space. Next problem up, I'm looking at number 4. So if I play with this, I'll say this is 2s plus 2 over. And if I complete the square, that's s squared plus 2s plus 1 minus 1 plus 5. That is twice s plus 2 over s plus 1 squared plus 4. And if I look at the table, I'm trying to figure out where I have something like that. It looks like it is s plus 1 squared plus 4. S plus 1 squared plus 4. Well, this is what I notice. There are things like that, and it's actually right there, but I'm going to show you a short way of doing this. That is, if I look at those two, I notice it's s squared, a squared, s squared, a squared. So, if I really want to take the shift, that's where I would use what I took off. I had the shift is right there. That is number 14. This is what it says. It says if you're going back, if I'm applying the inverse Laplace transform on this. So Laplace transform will get me f of s, and the inverse will take me back to f of t. Well, it says if you could shift the function, that's simply e to the ct, and then you have to do the inverse on f. If you notice here, I could factor a 2 out. Wouldn't that be s plus 1 over s plus 1 squared plus 4? And do we agree that if I'm looking at this, e to the negative t, remember those are opposites, will make this 2 over 2s over s squared plus 4. That's how we take care of a shift every time. Something you should really consider. I know you could match this problem, number 4, and there's one of these properties that matches exactly, but that's not going to be the case pretty soon. And now if I look at those, I notice this has an a, but this has an s. So it has to be a hyperbolic cosine. I need an s squared minus a squared. Well, if I look at what I have, s squared and a is 2, right? So that would yield the hyperbolic, there's a 2, and the hyperbolic cosine of 2t. And that would be my final answer. That's what you apply the Laplace transform on to get this mess. Something you should really start playing with that. And it was hyperbolic, right? It was s squared minus a squared, right? S squared. Oh, plus, I'm sorry. Plus. Plus, I pointed to the wrong one. If it's a plus, then I'm really pointing to the cosine of at. Not hyperbolic. That's coming up. So something that's going to take a bit of time to get used to. If I look at number 16, I'm sorry, if I look at number 6, I'm so stuck on that. Number 6, if they give me f of s, that means I'm working backwards. I want to find the inverse Laplace transform. But we have an issue. I don't have anything that matches this in the tables. So what I do, I actually try to break this up if I could and figure out where this came from. I would say this would be, this was from the table. This is not number 14 in the book. This is number 14 in the table. I'm going to mark those in orange. So if I look at this problem, I would say, well, let's see. Where would 8s squared minus 4s plus 12 come from? Again, the reason I'm doing this, I don't have one of those in the table. So partial fraction decomposition. And if I let s equal 0, I'll get a 12 equal 8 times 4. So a is 3. And if I continue on and say 8s squared minus 4s plus 12 equals a plus b s squared plus cs plus 4a. That would indicate that 8 must equal a plus b. Since I already found a, 8 equals 3 plus b, so b is 5. And if I take 4a, I already done that. If I take negative 4s, set that equal to cs, I will get that c equal a negative 4. So what this means, I can write this as 3 over s plus 5s over s squared plus 4 minus 4 over s squared plus 4. And I'm really applying the inverse Laplace transform on this. And let's see how this works. I'll get this to be, and let's figure this out. 3 times, let me use red, plus 5 times minus 4 times and let's see how this works. If I'm looking at that table, and you should have that table handy next to you, 3 over s. If I look at the table, 3 over s, the 3, the constant will come up, there's s. Isn't that a 1? If I look at s over s squared plus 4, so this is by 1. S over s squared plus 4, s over s squared plus 4, cosine of 4 is 2 squared, cosine of 2t, and that was by 6. So you make sure on the homework and the exam you number those for me. And if I look at, actually here I do need the 4. Sometimes you do, sometimes you don't, right? If I leave the 4 in there, and why is that? Because when I look at s squared over 4, if I look at s squared plus 4 in the denominator, it's right there. There's only one of each. and that's going to go to a sign. But do you see what the condition is? If this is squared, I need what you square to get that, which means I need to really take the 4 and make that 2 times 2. Put a 2 up front, and 2 over s squared plus 4 would be the sine of 2t. So this section is going to take some time to get used to, but it's not that hard once you get the hang of it. That's not 6, that's 5. So you make sure you number those on the homework. I'm not really as concerned on the homework, but on the exam, I must see the numbering.